Hello, welcome back. Today I'm going to start a new series. It's a textbook written in 2014, inspired from lectures from 2010. There's a preface, and it's called Understanding Machine Learning by Shai-Shalev Schwartz and Shai Ben David from Theory to Algorithms. There are lecture videos in 2015. While this is released 10, 11 years ago, it is a beautiful textbook. It is written nicely, and there's many important key concepts to understand. So while people say machine learning is developing very fast, I believe this book is very fundamental, especially in theory. And I'm going to just talk about the introduction, the story, and the motivation behind machine learning and why we need it. So it asks these questions like what is learning? What are the types of learning? And these questions are very important to really grasp, think of ourselves, what examples we can make, because this will increase our own view on this subject. So the first example they go through is bat shyness on rats. And essentially, whenever rats they encounter new food, so consider this as new food, what they do is they'll taste the food. And if they get sick, then they'll never ever taste that food ever again. However, if it's fine and they're healthy, then they will. Now, what are the problems about this? You have to taste every single food. And one problem is this is considered as learning by memorization because you really don't know whether this food or this food, while they look the same, they're pretty much different. And you taste this, you get sick, so it turns out you don't know whether this food is sick or not. And we call this generalization. And what I like to think of it is like, what if you learn a skill? Like, what if you learn multiplication? Like 3 times 3 is equal to 9, and so on, like your times table, right? One way you can learn multiplication is you have all these times tables, like 1, 2, 3, 1, 2, 3, and you basically just memorize the table, like 2 times 2 is 4, 3 times 3 is 9, and you kind of memorize this. But this clearly will not generalize to further examples that are much harder. If someone asks you what 33 times 13 is, and you don't have this memorized, then this is going to be a problem. So we call this property that we desire in machine learning generalization. Then they go through another example called pigeon superstition. And I've seen a video about this. I don't know if it's like a rooster or a pigeon, but essentially what it is like you give the pigeon some kind of action and it does it, then you're going to give some kind of reward. And this reward is going to be good. Think of it like chocolate or candy or whatever food you desire. And they figured out that when pigeons keep doing this action, they're going to keep getting the reward and it's going to be happy. So it keeps does it, and we call this reinforcement learning in some sense because we're taking an action and we want to get this reward by keep doing that action. So that is a different type of learning. And the textbook goes through a next situation where it tries to combine these two ideas with rats and whether you can reinforce it to learn something. And essentially, they do it. I don't know whether this paragraph, I haven't read it, like, it's my first time reading it for a while, but if I remember correctly, you do it with one example. It might not be the case, but you do it with one example, and it turns out it doesn't learn it. And a natural question we might ask is is one example enough? Well, clearly not. So how many examples do you actually need to learn the whole entire thing? So these are some things and some some desired qualities we might want is we might want things like prior knowledge, we might want it to generalize, but outside of this textbook, I like to think of it in 10 or 11 properties, and I could categorize it. What we first think about is performance. Is it accurate? Is it correct? Does it generalize well? Is it robust? Meaning that if you get some kind of noisy, incomplete data, is the performance still going to be good? So I like to call this performance. And what about practicality? Because eventually we have some kind of model here and we want to deploy it into the real world for some real world task. For example, some common models these days is deploying an LLM to model language. And you might want to ask with this, is it efficient? Does the model scale fast? Is the language text prediction going to happen quickly or is it going to take hours? Is it scalable? Meaning that when you increase computation, you increase space, you increase Your resources, will it scale? Is it simple? We'd prefer models these that are simple, that work, over ones that are extremely complicated. And this preludes to the next one. Is the model stable? Will it work in 10 to 15 years, or will it not? Another category that I especially am very interested is trust. Can you understand these models? Or is it interpretable? Is it fair? And is it like, can you quantify the fairness, the bias, and all these kind of stuff? And lastly, which is very important, is data. For example, data efficiency. Can you achieve good performance with only minimal data, where you don't need too much data? Or, for example, how many examples do you need? One example is clearly enough. Do you need 10,000 examples, or do you need a million examples? So how many examples do you need to truly learn? And on the last topic of learning is, what is learning? This book likes to say that learning is, you have some kind of experience, and from that experience, you can learn some kind of expertise. And I like to think of it as like, what is machine learning? Well, machine learning is, you have some kind of data, and from the data, you can learn patterns to make some predictions. I will tie this to future things, but machine learning essentially is in the intersection of statistics, which is kind of like the theory and the study of data, and computing science, which is the study of computational systems. So if we have computational systems that can learn from data to make predictions, we essentially get machine learning. Okay, so further on, we might ask, well, why do we need machine learning? Why do we need machines to learn from data to make predictions? What exactly? Well, to simplify in three ways, some tasks might not we might not be able to do it with our human capabilities. We might have a lot of data, tons of data, where a human, if they had a lot of time, can plot the data. Maybe the data was plotted something like this, and then the human can find some kind of polynomial prediction function like that to then make some kind of prediction, maybe somewhere here. But humans don't have that time, and they don't have that memory or the capacity to plot all this data, where in machines we can easily do it. Another reason is that some tasks might be too complex to program. For example, if we want to do things like self-driving cars, are we really going to make a program that has all input-output pairs for every single scenario where a car can what a car can do? In fact, there might be infinite many scenarios, because a car might go here, 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 or it can go here, here. Now, what if it goes here and there's a person there? Now, the person's crossing. There might be infinitely many ways that can happen. So you physically can't have all the input outputs of a normal computer program to do self-driving cars. That is not impossible. That is not possible. And lastly, which I think is really important, is adaptivity. One classic example of when you need to use machine learning is, say we have some kind of movie website and we want to create some kind of user recommendation so that it appears on the front feed. The data is that the user watches these movies, and we can see which genre it watches, what topic it watches, what review it gives. This is our data, and then we can learn a prediction on what movies it might want. But what happens if this user, instead of watching like these fantasy fictional movies, it now watches, I don't know, maybe some documentary, some kind of sci-fi documentary? We need our programs to adapt to what the how the data changes. And a good example is like, the world always changes, users change, preference change. So this is, I think, like one of the most important reasons of why we need machine learning. Then we talk about different types of learning, and this will go further, but what I like to think about, and you can definitely read this chapter, is I like to think about what type of supervisor we might have. We might have a supervisor, we might have no supervisor, we might have semi supervisor. what if we have something called self-supervisor? Or what if we kind of just experience the world, we see what kind of reward we get or punishment, and then we like update, okay, maybe if I got a punishment, I don't do this same action again. Or maybe if I got a reward, if I was in the same scenario, I do the same action. So there are many ways to learn. A lot of that is self-explanatory. I'm not going to go through it. Other ways is that we might have active or passive. I like to say, how does the model react? How does you react? How does the agent react? Are you just getting a bunch of data? Are you just getting a bunch of data feed into your model? Or are you physically reacting with the world and then updating yourself? So that is like the difference between passive and active. And then the helpfulness of the teacher. For example, let's say you're trying to learn how to swim, and your teacher is like a professional swimmer, or it's like a lifeguard, or just like a swimmer in general. Then we like to call this like an indifferent learner. Like you clearly are getting some advice, it's either helpful or not, but they kind of want you to learn. Another type of learner might be adversarial. It could be someone who's not a swimmer, or it could be someone who doesn't want you to know how to swim. Maybe they're jealous. So these are different types of learners. And finally, we might have something called online or offline or batch protocol. I just call this the data processing. So is your data coming from somewhere? Is it offline? Or are you interacting with the world like it's online? Finally, I touched on this a little bit, that machine learning is connected to a lot of fields: CS, psychology, information theory, statistics. You can go on and on and on. But I like this blurb here because of its connection with statistics. One disclaimer I like to make is I feel like the field of stats and the field of machine learning are almost co-joined together. But there was a time, maybe around this time, where they were a little bit separate and they had differences on their ways of thinking. And one way of thinking of statistics is that statistics, they like to have this thing called hypothesis testing. You have some kind of claim, some kind of other claim, alternative claim. You want to test this claim based on new data. However, in machine learning, we really want to learn a rule, a prediction from our data. So we're not testing on new data, we're really learning from our data. This is one way that's kind of different. Another way that's different is this asymptotic behavior. In statistics, we really like to take our sample size to infinity. One of the most important theorems that you might ever know is the central limit theorem. And if you read more about that, that's an asymptotic behavior as the sample size goes to infinity. However, whenever we're learning from data, like machine learning, our data will always be finite. You can't experience infinite things in the world. At some point, you're going to have finite amount of data. Now, nowadays we have tons of data, and especially in these language models. But regardless, it is still a finite data study. Another difference is our distribution. In statistics, we like to have a model that seems very close to our scenario. For example, if we take the heights of people in the world, it seems very close to a normal model. And then from this normal model, we can maybe infer different things about the true population. Another model we might have is like the Poisson distribution or the gamma distribution. Howeas in machine learning, we like to think of this as distribution free. We don't know what distribution it has. Maybe it has some distribution like this. We want to eventually learn some kind of distribution so that we can make some predictions. Now, these are the differences. It'll talk more about this later. Disclaimer though, I think that these communities are really meeting together, and now we're using stats to really advance this ML theory, so it's very circulated. Lastly, this book talks about how to read this book. I will go chapter by chapter, and you can for sure see the notation over here for more information. Thank you.